Hello, in this video, we are going to discuss Newton's laws of motion. To clearly understand what this law means, let's look into the concept of force. Force is essentially a push or a pull that one body applies to another. If you push somebody, you exert force. If you pull somebody or anything, you still exert force. It's a fundamental concept that can change the state of motion of an object. For instance, think about how you push a door to open it or pull it to close it. Those are simple examples of force in action. The unit we use to measure force is Newton, represented by the letter capital N. This is named after Sir Isaac Newton, who made significant contributions to our understanding of motion. Remember, when we talk about force, we're discussing something that drives change and interaction between objects. It is a key element in the laws of motion that we are about to explore. Forces has two general types: the fundamental forces or the basic forces and the non-fundamental forces. The first fundamental force is the force of gravity or the gravitational force. It is responsible for the weight of every object on Earth. It is the reason why we stay grounded and why a ball returns to the ground when tossed in the air. Consider this. It's not just about weights and balances. Gravitational force orchestrates the grand dance of celestial bodies, keeping planets and other celestial bodies in orbit around each other or around the sun. Let's remember, while we often feel its effects through weight, gravitational force is also a cosmic player. The next fundamental force is the electromagnetic force. This force is critical because it holds the atoms and molecules together, essentially forming the building blocks of everything around us. It's the reason why matter is stable and why we can experience the world in a tangible way. Let's think of this. Without the electromagnetic force, atoms wouldn't be able to bond, and life as we know it would not exist. As we explore these fundamental forces, remember that each plays a unique and vital role in the universe's structure and the daily phenomenon that we observe. The next fundamental force is the weak nuclear force. What makes intriguing on the weak nuclear force is its unique ability to change the type of particle, leading to the transformation of a neutron into proton or vice versa during the radioactive decay. This transformation is crucial for the balance of elements in the universe. The last fundamental force is the strong nuclear force. This one plays a crucial role in holding the nucleus of an atom together, binding protons and neutrons tightly. Consider how essential this force is. Without it, the nucleus would simply fly apart due to the repulsion between protons. So the strong nuclear force is what keeps the core of an atom stable. It operates at a very short range, but it is incredibly powerful, much stronger than the electromagnetic wave. There are three examples of non-fundamental forces, namely the push, the pull, and the friction. There are two other types of forces, contact force and non-contact force. Contact forces occur when two objects are physically touching. This interaction is essential to many everyday occurrences, such as when we push a door or when friction slows down a sliding book. The key takeaway here is the necessity of physical contact for these forces to exist, whether it's gentle touch or a firm press. The interaction always requires contact. Remember, contact forces are all about physical connections between objects. Examples of contact forces: friction, tension, normal force, elastic force, and applied force. Next, we'll explore non-contact forces, which are quite fascinating as they act over a distance without direct contact. This is a result of the interaction between two objects that are not physically in contact with each other. A concrete example of a non contact force is the gravitational force. Let's delve into the concept of free body diagram. It is a powerful tool in understanding forces. First, we'll consider how to construct it. Imagine isolating an object from its surroundings. This helps us focus solely on the forces acting on it. Choose the object. Start by identifying the object you want to analyze. This is your point of focus. Then you identify the forces. Consider all forces acting on the object. It's key to ignore any forces it exerts on other objects. The third one is the direction. Determine which direction each force acts. This will guide your diagrammatic representation. Then you draw the arrows. Use arrows to represent forces since it's a vector quantity, starting from the object and pointing outward to indicate the direction. And lastly, you label the arrows. Label each arrow to specify the force it represents. Here are some examples that you may try drawing or constructing free body diagrams. Now let's look into the Newton's laws of motion. Let's look into the first law of motion, the law of inertia. It states to us that an object at rest tends to remain at rest and an object in motion tends to remain in constant motion along a straight line path unless acted upon by a net external force. This law tells us that an object at rest will stay at rest and an object moving at a constant speed will continue moving in a straight line unless it is influenced by an external force. It is the natural tendency of an object to resist changes in their motion. Think of a parked car. It won't move unless someone pushes it. Similarly, a rolling ball will keep rolling on a smooth surface until something like friction or a barrier stops it. Let us remember that inertia is about consistency in motion or rest unless something else comes into play. Here an example of the law of inertia. Inertia is the reason why we wear seatbelts. They help apply the external force needed to stop us safely in a car. So buckle up for safety. Here is another example of a law of inertia. Let's take note. Object tends to keep doing what they are doing. Let's check your understanding. Try to answer this. If you are in a spaceship and fired a cannonball into space, how much force would have to be exerted on the ball to keep it moving once it has left the spaceship? Let's move on now to the second law of motion. The second law of motion states to us that the acceleration produced on the body by a force is directly proportional to the force and inversely proportional to the mass. Writing this in an equation form, we could have F, which is the force, is equal to m, which is the mass, multiplied to the acceleration, which is a. Here, it is clearly stated that as the mass increases, we need to apply a greater amount of force if we want to come up with a constant acceleration. The acceleration and mass are inversely proportional. As mass increases, acceleration decreases. Let's have a look into this example. A 4-kilogram watermelon is pushed across the table. If the acceleration of the watermelon is 2.4 meters per second squared to the left, what is the net external force of the watermelon? Here, we are given that the mass is equal to 4 kilograms. Then the acceleration is 2.4 meters per second squared. We are required to find the force. Our equation is that the force is equal to the mass times the acceleration. For our solution, we have force is equal to mass times the acceleration. Writing it and substituting the given values, we have 4 times 2.4. Here, the force is now equal to 9.6 newtons. So that's our final answer. Let's go to another example. A net force of 15 newtons is exerted on an encyclopedia to cause it to accelerate at a rate of 5 meters per second squared. Determine the mass of the encyclopedia. Here, we are given that the force exerted is 15 newtons and the acceleration is equal to 5 meters per second squared. Here, we are required to identify the mass. It's the same equation, F is equal to ma. To solve this problem, we write our given equation and work with our working equation. We divide both sides by a, so we cancel it out on the right side. So we have m as isolated is equal to F over a. Substitute the given values. F is equal to 15 newtons and a is 5 meters per second squared. Let's take note that Newton is equivalent to kilogram, Newton, or kilogram, meter per second squared. Here, we can cancel out meters per second squared, and the remaining unit is in kilogram, which is the unit of mass. So 15 divided by 5 is equal to 3. So we have 3 kilograms as our final answer. In the second law of motion, let's take note that the mass is the amount of matter in an object. Wherever we go, wherever we are, our mass remains the same. But the weight changes depending on the force of gravity or the gravity that is present in a planet or in an object. The weight is the gravitational force acting on an object. We have here that F is equal to ma, which is moving along the horizontal axis. If we are going to look for the weight, we may change F into Fg, and A, acceleration, will be changed to acceleration due to gravity. It is equal to 9.8 meters per second squared downward. Let's have this example. Amelia, the ballet dancer, has a mass of 45 kilograms. What is Amelia's weight on Earth? What is Amelia's mass on Jupiter? Where acceleration due to gravity is 25 meters per second squared. And lastly, what is Felicia's weight on Jupiter? Solving this problem, still we need to identify what's given. So we have 45 kilograms as Amelia's mass. The acceleration due to gravity on Earth is 9.8 meters per second squared. And the acceleration due to gravity on Jupiter is 25 meters per second squared. We are required to find the following: the weight of Amelia on Earth and the mass of Amelia on Jupiter, and the weight of Amelia in Jupiter. So to solve the problem, we just need to write down again our equation and transform and substitute all the given values. So we have the mass, WE, which is the weight of on Earth, which is equal to mg, where g is 9.8 meters per second squared. So we multiply it to 45, and we can come up with the weight of Amelia on Earth equal to 441 newtons. So to identify now the mass of Amelia on Jupiter, so let's take note that the mass doesn't change wherever we go. So the mass on Jupiter is just equal to the mass on Earth. So that's just equal to 45 kilograms. So to identify Felicia's weight on Jupiter, so we're still going to use the same equation we used in letter A. So we have Wj, the weight on Jupiter, is equal to the mass times the acceleration due to gravity on Jupiter. So we have 45 kilograms times 25 meters per second squared, giving us that the weight of Amelia, that's Amelia, is equal to 1,125 newtons. So let's try. You try. Answer this problem. Suppose that a sled is accelerating at a rate of 2 meters per second squared. If the net force is tripled and the mass is doubled, then what is the new acceleration of the sled? You try it. Now let's move on to the third law of motion, the law of interaction. It states here that for every action, there is an equal but opposite reaction. This means that if one object exerts a force on another object, the second object will exert an equal and opposite force back on the first object. This law tells us that whenever one object applies a force onto another, the second object pushes back with an equal and opposite force. Equal, meaning they have the same magnitude. Opposite, meaning they have different direction. It's fascinating how this principle governs so many everyday situations, from walking to driving a car, anything. Think about this. When you push against a wall, it pushes back with the same force even if it doesn't move. This interaction is what keeps us balanced and allows us to interact with our environment effectively. Let's keep this in our mind that this principle, as it forms a cornerstone for understanding more complex interactions in physics. The law of interaction is everywhere. Here are some examples. The law of interaction is also known as the action-reaction pair. So here, the first one is a car moving to the right. Here, right, drawing an arrow, the free body diagram on the tire pushes the road, then the reaction on here is that the road pushes on the tire. Another action-reaction pair, we have rocket pushes on gas, and the gas pushes on rocket. Then we have a man pulls on spring, and the spring pulls on the man. And the last one is that the earth pulls on the ball, and the ball pulls on the earth. So that's Newton's laws of motion. I hope you learned something. Thank you, and have a nice day.